processes, and we've also talked a little bit about how they solve. So once again, just to recap, there's 3 cases for this, and or no, it's polytropic, not isotropic. Sorry, I was thinking of wood. Wood is anisotropic. It's polyotropic process. My bad. So polytropic processes. So we talked about work is equal to PdV, and we talked about the different cases for how you solve these. And if you know that n is equal to 1, 0, or something or else, they follow this. So this right here is if n is equal to something other than 1 or 0. You use this right here. And it ends up being this formula. So work is equal to this, which is P2V2 minus P1V1 divided by 1 minus n. Oh, no, this one's the one for n equals 1. Sorry, my bad. I was reading wrong. And then the next one for, or no, it was for n equals something other than 1. Sorry. This thing is, oh yeah, it's valid for all cases except that. Sorry. So the first case is for n is not equal to 1 or 0. The second case is n equal to 1, which is this logarithmic one. So if you have work and if you know n is equal to 1, which is usually either given or you can find that, then you go and you just plug this in right here. For work is equal to P1V1 times the natural log of V2 over V1. Then the last one is pretty simple. Pressure stays the same, so it's just a very simple work is equal to pressure times the change in volume. And really quickly, this volume can be specific volume, or it can also be total volumes. It can be what it is now, total volumes, or you can divide by mass and get specific volumes. So that's sort of what we talked about last time. And we skipped a lot of this stuff because it's just other examples of work, which we don't really need to talk about. It's kind of not useful. And then we also talked about this. This was the internal energies, the kinetic energies, the potential energies of last time. So essentially the total energy of a system is equal to the internal energy difference plus the kinetic energy difference plus the potential energy difference of 2 state points, right? Which can also be summarized as the following. Delta E is equal to delta U plus delta KE plus delta PE, right? And now we get on to the next topic, which is heat transfer. So heat transfer is the next type of external or internal source of heat or energy that's going to come into a system, okay? So, as I said last time, heat transfer is coming from somewhere. We don't really generally care where it's coming from. We just know that it's heat transfer and it's coming and it's doing something. It's heating something up or it's leaving a system and cooling it down, right? One of the two. And so, for this one right here, this is a cylinder with gas in it. And what's happening is heat is being sent through this. It's heating up the bottom, which is coming inside in energy, right? It's heating up the gas. That gas is gaining energy through heat transfer, and the gas is, changing properties, right? So from one state, the gas is at equilibrium, right? Let's say there's no heat transfer coming in yet. Gas state here, doing nothing. Then we turn on the heat and we get it heated up. Then the second state is after the heat transfer has taken place. So that's kind of how this plays off. So, and heat transfer has the same units of work. It's kilojoules per kilogram. So it's in terms of energy. It's joules, right? Or kilojoules, megajoules, things like that. And now let's talk about the sign convention. So let me get Epic Pen out because I always forget to open this thing. So we're going to talk about sign convention. So sign convention is the opposite of work. And what I mean by that is that heat transfer to the system is positive, right? Heat transfer from the system is negative. So think about it this way. If heat transfer is coming into the system, right? It's kind of a different way of looking at it than work. Not exactly opposite, I would say, but it's a different way of looking at it. If heat transfer is coming into this cylinder right here, right? If it's coming into the cylinder, that is a positive heat in. Because we are adding heat to the system, right? Essentially, we are taking energy from outside the system and putting it inside, right? So now think of that in terms of work. Remember when we used to add work into the system, it was a negative concept, right? So when we added work into the system by virtue of like some paddle wheel or something, if we just added work in, it's a negative concept because it is work we had to put in. Heat transfer works in the other way, is that when we put heat in, it is positive. Heat leaving is negative. So think about it like this, is that think of your house. When heat enters your house, we are treating that as a positive value. Your house is gaining heat. And then during the night, when outside is cold and your inside is hot, warmer than outside, heat leaving to the outside is negative. Okay? So like I said, it's a sort of inverse of heat transfer, right? Or inverse of work, sorry. And so what we use in this class is we use the symbol Q to denote amount of energy coming in through heat transfer. That is transferring across the boundary, okay? And as I said, the sign convention is as I said. So the sign convention for heat transfer is the reverse of work, okay? All right. So right here, now we talk about how, about more specifics about heat transfer. So heat, just like work, is not a property. A property are like things like what, like volume and temperature, pressure, things like that. Work and heat transfer are not properties, but they can be represented as by properties. So for example, two internal energy values subtracted can be equal to heat transfer, but heat transfer itself is not a property, okay? And then it says, let's talk about this. So the amount of energy transferred by heat for a process is given by the integral of Q is equal to delta Q. And where the limits from 1 to 2 are state 1 to 2. And do not refer to the values of heat at those states. So just like work, it is not work from 1 to 2, or state, you know what I mean? It is state 1, their values, versus state 2, their values. So for example, if I have 10 kilojoules of energy at state 1 and I have 50 at state 2, and the only thing that happened in between is that heat came in, well, very clearly that heat entered at 40 kilojoules, right? To add 40 to the system. So that's what it means, that essentially heat is coming in the interim. It's coming in between states 1 and 2, right? And that's like the process that drives 1 to 2. And we'll probably do an example today that shows you a little more about how we like to do state points and how they relate to heat transfer and that. All right, and then it says, as for work, the notion of heat at a state has no meaning, and the integral should never be evaluated as Q2 minus U1, the same one as work. And it says the rate of heat transfer is denoted by Q dot. In principle, the amount of energy transferred by heat during a period of time. It's the same as the work one. The dot means that there is a per time unit. Q by itself means that there is no time unit. It's just mass, right? It's just something without time. It's something that happened right there. All right, and then just like work, it represents the area on the boundary of the system where heat transfer occurs. The units for heat transfer Q and heat transfer rate are the same as though introduced for work and work dot or W dot. The units for the heat flux are those of heat transfer per unit area, are known as kilowatts per meter squared or BTUs per hour foot squared. So this is a heat transfer concept that we won't see much in this class, which is heat transfer per unit area, which is the heat flux. We don't use heat flux in this class. We use just like a kilojoule. So a kilojoule, so think about it this way really fast. So work, right, we have this in terms of joules, right? Or kilojoules, right? W dot is in terms of kilowatts, which is equal to a kilojoule per second. So do you see, essentially the dot represents adding a per unit of time to it, not anything else. So if you have a work that is that doesn't have a per unit of time, essentially how this ends up working out in this class is that a per unit of time is added if there's a mass flowing across the boundary. So like for that, that cylinder with the gas in it, there would not be a time attached to that. So it would just be whatever the mass is. There would be no time, so you would use kilojoules. If there is a flowing amount of mass coming from 1 second to another second, then you usually use kilojoules per second. So those are the units. Essentially, the dot represents time, and there must be a time somewhere in the units. Hopefully that makes sense. And then right here, this is a good question, probably going to be on your homework, the word adiabatic. You'll hear this a lot in this school. Adiabatic means that no heat transfer took place. So if I said something like an adiabatic process from states 1 to 2, immediately what that should tell you is, in your head, you should go adiabatic process. That means Q, or Q dot, is equal to 0. Immediately, you should say Q from 1 to 2. The heat transfer from 1 to 2 is equal to 0, because I said it's an adiabatic process. Okay? So write that down in your skulls, in your heads. You guys got that written down? Nah, everybody's like not even typing. Everybody's got it. It's a boring Monday for you. Alright, cool. Alright. So then we have heat transfer modes. This is something that I'm not going to cover because we don't care about heat transfer where it comes from in this class. We just care about the number. So for example, heat transfer can come from anywhere in this class and we don't care. We just know that there is some heat coming in and it's equal to some number, right? So, but just for your information, I know you probably will be taking heat transfer. If you haven't already, you will be soon. Conduction's one, convection is another, radiation, right? These are the three methods of heat transfer, the three classical ones. And we're not going to talk too much about that because it's not worth it. But convection is when air flows across something, like a fluid flows across a surface. It's taking heat away or giving heat. That's convection. Conduction is when two things are together and one is hot, one is not, and they're shading energy across the contact. And then radiation is via, radiation, right? Radiative heating. And then it says, real quick, closing comments. The first step in a thermodynamic analysis is to define the system. It is only after the system boundary has been specified that possible heat interactions with the surroundings are considered. For these are always evaluated at the system boundary, okay? So that is an important thing to know. All right. So now this is where we get to our very first questions, really. So that polytropic process thing we talked about previously, that is a part of these questions, but this right here is the energy balance. So the energy balance is the important part, is that we are now, our goal in this section is to try and find all energy at every state. So that means kinetic, potential, internal energy, heat transfer, and work between the states. That is what our goal is to define all of those using things that we can find, right, on a table or something. That is our goal. That is our mission. So if you choose to accept it, right? So let me see where we need to be today. So it's the 24th today. We are doing 2.5. So good, we're on time. Wonderful. So this is what we're starting with. So energy balance for closed systems. So closed systems, as we talked about previously, closed systems are systems in which mass cannot flow through the boundary. It is essentially it's your water bottle with the cap on. That example I keep parroting back to you. It's that one. Nothing flows across it unless you open the cap, but then it's an open system, right? Literally. All right, and it says, as our previous discussions indicate, the only ways the energy of a closed system can be changed are through transfer of energy by work or by heat. Further, based on the experiments of Joule and others, a fundamental aspect of the energy concept is that energy is conserved. We call this the first law of thermodynamics, boys. We made it. It's the first law. So essentially, it just means that it's a conservation of energy, right? So here it is. We can talk really quickly. I'll just do a really fast one. So it says we'll skip past what his actual experiment did, but essentially what it is saying is that based on his experiments, Joule deduced that the value of the network is the same for all adiabatic processes between two equilibrium states. In other words, the value of the network done by or on a closed system undergoing an adiabatic process, no heat transfer, between two states, given states, depends solely on the end states and not the details of the adiabatic process. And it says if the network is the same for all adiabatic processes of a closed system between a pair of end states, it follows that the definition of property, the first one, that network for such a process is the change in some property of the system. The property is called energy. This process is called energy. Following Joule's reasoning, the change in energy between the two states is defined as this. So energy 2 minus energy 1 is equal to the work. Essentially the work that had to be put in. And now, really quickly, you guys are probably wondering, you're like, well, wait a minute. If there is heat transfer, then where does it fit in? It literally fits in right here. It's plus Q. But because this was an adiabatic experiment and no heat transfer, Q went to 0. And so that means the only energy change in a system had to be done by work. It is done by nothing else, right? So think of it this way. If you have your water bottle and it's resting on your table, that is state 1. It is at, let's say, energy level 1. And then you pick up your water bottle and shake the hell out of it, right? You're putting in, we'll just say that you're putting in work to it, or you're stirring it up. Let's say you stirred it up using some mechanism, and no heat transfer has flowed into the boundary. And then we got to energy level 10. What you would say is, well, energy level 2, which is 10, minus energy level 1, which is 1, is equal to 9. That means that there was 9 units of work put in between there. That is what this is saying. It is saying that the amount of work going in, if there is no other processes taking place, has to be equal to the total change of energy. Hopefully that makes sense, right? I'd like some yees in the chat, if possible. Alright. So, hopefully that makes sense. Alright, and then we have summarizing energy concepts. So, on the left side of the equation, we have change in the amount of energy contained within a system during some time interval equals the net amount of energy transferred in across the system boundary by heat transfer during that time interval. And now remember, depending on the direction of the heat transfer, there could be a negative in front of this or a positive, right? You just have to be careful. And then it is net amount of energy, subtracting net amount of energy transferred out of the system boundary by work. So it essentially looks like this. Delta E is equal to Q minus W. Alright? And then you can rewrite this, obviously, where delta KE plus delta PE plus delta U, which remember was this, right? It was equal to this earlier, is now equal to Q minus W. So what this is saying is that the change in potential energy, so any kinetic energy we gained or lost, plus any potential energy we gained or lost, plus any internal energy change, has to be equal to the heat transfer minus the work's energy. So, I mean, more or less the idea of this is that if there is some energy change, something had to have taken place, right? Which that stands to reason, right? Like if you let it sit your water bottle on your desk and you do nothing but stare at it, has anything changed? The answer is no. Except now maybe your eyes hurt a little longer. They're a little watery. But if something is done to it, it's accounted for, right? Essentially any change in any of the energy values has to be accounted for in either heat transfer or work, and that is what this equation states. Which I think that's logical, right? I think you guys can pretty much follow that. Alright. So then we have important aspects of the energy balance. So it says various special forms of the energy balance can be written. For example, the energy balance in differential form, I guess we can write this, but essentially where dE is the differential of energy, a property, since Q and W are not properties, their differentials are written as, instead of dE, it's delta E. It's the delta. And then it says the instantaneous time rate of the energy balance is dE dt over Q dot, or minus, equals Q dot minus W dot. So essentially what they did here was they added a time. So instead of delta E, instead of, just delta E equals Q minus W, they added a time. So essentially now it's dE with respect to time. So the change in energy with respect to time, you have to remember add these dots at the top to show that there is a unit of time in these. Okay? So they took a time differential of energy, and that means that there has to be a time differential of work and heat transfer that follow it, right? Hopefully that makes sense. Alright. So then it says the rate form of energy balance is expressed in words. the time rate of change. I just talked about this, but essentially it's the time rate of energy change, the net rate of energy being transferred by heat minus the net rate that energy is being transferred out by work. It's just the same thing, just with time added in, okay? And then you have to do the same thing for all the other ones, right? So, remember, you just have to add a time for all of these. So dt, delta ke, delta p, or dpe, du, dke, over to dt, right? But this doesn't really get, so this right here is just for your information. It doesn't really accurately, it doesn't reflect what you will be doing. You're not going to be writing things like this. What you'll be writing is, the units will take care of it for you. And what I mean by that is, you'll have something like, let's say it's an open system. There would be like some mass of, let's say, 1 kilogram a second, right? And if you're multiplying in to what this is right here, our units will be in terms of kilojoules per kilogram, because that's what the table finds. So let's say it's a 10 minus 5 kilojoules per kilogram, right? Let's say there's some mass attached to it. You'll see that the kilograms will go away and you'll be left with kilowatts, which is a what? It's an energy per time. So essentially this dt part will be taken care of by the units for you. Now, if this was just a mass, a closed system, you would have 1 kilogram, which would what? You'd get rid of the kilograms and you'd be left with kilojoules, which is a not time-related energy. So the units will take care of this for you. You don't have to worry about this dt stuff. The important thing is you need to know when it's an open system and when it's a closed system, okay? That's the importance, is that the units will take care of it for you once you understand what system you're working in. Let me see, this is important. Probably not so much, really. Alright. Let me see. Alright, so here we have, using the energy balance, process of a closed system. So we're about to do this example, everybody. So everybody get your thinking caps on, alright? Thinking caps on. I'm still waiting for someone to post the first GIF into this chat. It didn't take the last class very long. So, 4/10, so here it is. So this is cooling a gas in a piston cylinder arrangement. So let me see if I can find a picture of this. So right here. So this is the piston cylinder arrangement, right? And so what they have given you here. So this is how you should start these questions. It says, 4/10 of a kilogram of a certain gas is contained within a piston cylinder assembly. So what they have just given you right there, guys, this should be the first things you do, is you should write out, I'll actually open up something here. Let me see. I'm sure you could. Paint 3D. I'm actually going to pull up something here. This might help us. So this is the first thing you should do to start this off. So I'm going to go ahead and make this smaller. So what you should do is, the very first thing is that you should go, all right, 4/10 of a kilogram. So what they've just given you was the mass. So they did 4/10 of a kilogram right? I just like to write it out exactly as they say it. You see fit to however you want to do it. It's 0.4 kilograms, right? But I'm just writing it out as I see it. And then it says, the gas undergoes a process for which the pressure-volume relationship is this, right here, PV to the 1.5. So what they have given you is that they've said that this is a polytropic process where PV to the N equals constant, where N is equal to 1.5, right? This is all the things they've given you so far. And then it says the initial pressure, so P1, is 3 bar. And then it says the initial volume is 0.1 meters cubed. So volume 1 is 0.1 meters cubed. Okay? So this is what we're working with so far. Let me move this over. And then it says the final volume is 0.2 meters cubed. So I usually write this over here. You do V2 is 0.2 meters cubed. And then obviously we don't know P2, but we will probably need to find that, I would assume. So, like I said, leave spaces for all the other things. And then there's one more thing that they said. It says the change in specific internal energy of the gas in the process, U2 minus U1, is negative 55 kilojoules per kilogram. So, what they gave you was, this is delta U of that kinetic energy equation we saw earlier. Its delta U is negative 55 kilojoules per kilogram. Now, really quickly, this does make sense, right? So this is where you need to start developing these things in your head. This does make sense because remember, the question is cooling a gas in a piston cylinder. Also, it went from a smaller volume to a larger volume, right? Would you guys agree? And energy, as you can see here, has left. We have lost internal energy, which means what? You guys would probably agree that very clearly, if you use your head, we have gained volume, which means the pressure is lower, temperature was lower, right? And we also lost energy in terms of internal energy of the fluid, which means that cooling makes sense here, right? If we gained a bunch of energy from one state to the next and it said it was cooling, we didn't cool it. I'll just tell you that now. You have not cooled it if we have gained a bunch of energy. So we have lost energy, we've gained volume, therefore it stands to reason that we have this right here is a cooling, and it makes sense. So this is where you guys are going to have to start developing these things in your problem solving. By looking at changes in state 1 to 2, things have to be able to click to you and make sense. Does everybody see how I explain that, and does everybody understand like what I mean when I say that? Okay. Tanner speaks for the rest of you. Because it's important that you develop this, because there are some people that get later on into the class and they can't tell when heat transfer should be leaving or entering based on properties they've obtained. They have no idea about how it makes sense. And so I want you guys to develop that early. You have to be able to know, like when you see internal energy being negative between a process from state 1 to 2, it means we lost energy, number one. Essentially the energy of the fluid went down by 55 kilojoules per kilogram. The volume also went up, which means in a piston cylinder, it got bigger, which means that the pressure got smaller as we moved. So the second pressure should be lower than 3 bar. And when we find that pressure, you will see that it should be lower than 3 bar. And if it's not, something is wrong. All right, so I'm going to go ahead and get rid of this for now. So right here is a picture of the question. Obviously, they do it on PV diagram, and as you can see, state 1 is here. So we have high pressure, low volume, right? That makes sense. So if you look, this is another thing you guys have to learn, is these PV diagrams and TS diagrams, is that you have to follow the states. And this is really important because state points are extremely helpful. If you follow the states and the units, you will be successful. So state 1 is up here. It is high pressure, low volume, right? Which makes sense because in a piston cylinder arrangement, the smaller this is, the higher the pressure it is, right? But so essentially volume and pressure are inversely related here, right? So as the smaller the volume, the pressure goes up. So right here we have a small volume, but a smaller volume but high pressure. And as you can see, if we follow this down, this is that process we're going through, the PV to the 1.5 thing. This is the polytropic process we are doing. Then we reach state 2, which as you can see is lower pressure, right? Lower pressure, and also a higher volume. So essentially our piston, if this is the starting point, our piston ended up back over here. This is our new piston cylinder after state 2, or once state 2 starts. It should be moving backward, okay? Because the gas expanded. So let's move on to the next part of this. Let me get rid of these dots. All right, so real quickly, this is the first part. It says analysis. So an energy balance for the closed system takes the form. So if we look in the question, I'm assuming it said that we need to, does it say anything? Yeah, so right here, this is another thing that I didn't mention because I overlooked it. It says there are no significant changes in kinetic or potential energy. What that means is that delta KE and delta PE go to 0. This is a very common thing in this class where we get rid of those immediately, okay? So everyone, make sure you look out for this. Don't be like me. I would have assumed it probably later, but be very mindful of how you see these, because sometimes they're not. Sometimes they are added. So this is the energy balance right here. And so, if you use our total energy balance, it is, remember, that equation of delta KE plus PE plus delta U is equal to Q minus W. So, with these two going to 0 because of the question saying that kinetic and potential energy effects are neglected, we are left with only this part right here, which is delta U is equal to Q minus W. So essentially, the change in heat transfer is equal to the heat transfer minus the work input, right? In terms that we are understanding. And so, really quickly, we know this one, right? Delta U was given to us in the question. So this is how you need to start approaching these things. Delta U was given to us. It was given as negative 55, if we remember here. Delta U is negative 55 kilojoules per kilogram. Oh, okay. So, okay, that's not exactly right. So these are overall U's, and what that means is that they are in terms of just energy, not per mass. But remember, we were also given a mass at the beginning. We were given 0.4 kilograms. So you can find that number just by multiplying in. But essentially, we've been given it. Delta U is taken care of, right? We have figured that one out. But now we need to figure out one of these two, right? One of them. Now, really quickly, this is a piston cylinder arrangement, which means what? Think of your car. When the cylinder goes from being here, like let's say, I'm just going to use an exaggerated example. Let's say it goes from being here to then being where it is now. Like let's say it goes from here and now back up to here. That means that there was some work that took place in there, right? Would you agree? Because remember, the piston is attached to something. It's shooting down and it's attached to the shaft. So some work has taken place here, which means that we can find a work. And now you're probably wondering, well, wait a minute, so what about heat transfer? Can we find heat transfer in this? The answer to that question is no. And the reason why we cannot find it is because, remember, heat transfer, it's a little more difficult to find, especially in something like this. You would have to be given the heat transfer here. And by the way, in other questions, you will be given heat transfer for this and told to find the other things, right? So essentially you can sub them out and, it's interchangeable. It just changes the process. But for this one, we cannot find the heat transfer. We don't have enough information to. But what they did give us was that this piston cylinder follows the polytropic process, right? That PV to the, 1.5. So what that means is that, so they went ahead and just changed the equation. So they did mass times U2 minus U1 is equal to this. So they just went ahead and plugged in the mass, which is what I said earlier, but we'll get to that in a second. So that means really fast, I'm going to go ahead and increase the canvas size. So really fast. That means that for our question, this is our box of knowledge. This is where we live, is in this box of knowledge, right? Everything we know is inside of here. Not a very big box yet, but it will get bigger, I promise. So, I really wish I had put that in a better spot. Anyway, so then we also know that delta U is equal to Q minus W, right? And then this one also transforms to U2 minus U1 is equal to Q minus W, right? We know this transformation. And so, now we need to find one of these two things. And I say we focus on the work because it's a piston cylinder and we know work has taken place and they've given us an equation to help us find it. So really quickly, this is where that polytropic process question we did the other day comes in. So our N for this question is 1.5. It is given in the question. So N is equal to 1.5. Does anyone recall what the equation for that was? The answer is probably no, because it's a very long one. So if you recall, there's that long integral using the 1 minus n and all that. And so if you know that since n is not equal to 1 or 0, you can just write work is equal to, and I will go back and pull that up because it's a long way home. Alright, I was on 50 something. I think I was on 58, so I'll go back and find this. Sorry. I should have had that one memorized in my head already. That we'd be having to go back. Oh man. Taking quite some time. Where's this at? I must have passed it. Yeah, I passed it, of course. Yeah, it's right here. It has to be. Yeah, next time I will do that a little bit better. So, really quickly, this is the equation that we're looking for, is right here. And so, you can memorize this one. It's really not that bad. These are pretty easy, but it's P2 V2 minus P1 V1 over 1 minus N. So this right here is for the case that N is not equal to 1 or 0. So if it's N is equal to anything other than 1 or 0, this is the case you use. So, and then, like I said, likewise, the case you use for if it's 1 or 0 is you change to this. So P1 V1 times the ln of V2 over V1 for that's case 1 or N equals 0. Then the last one is very simply the pressure doesn't change, so its work is equal to P times change in volume. So now that we've done that, let me make sure I remember that. Yep, I got it. All right, so now I'm going to go back to 58. All right, right here. So let's pull this up. So if we remember, our equation work is equal to P. Oh wow, I'm using. I was on the wrong one. Let me get back to this. So it is P2 V2. Oh, not a W. Sorry guys, it's my first day. P2 V2 minus P1 V1 over 1 minus N. Right? And so, when we plug in our numbers here, you'll find that we actually don't know P2 yet, because obviously we haven't found it using that other, using the initial equation. But let's go ahead and check mark it. We know, or we don't know P2, so let me go ahead and get rid of that. We know V2, V1, P1, and N. So we need P2. And how we find that is, it's the same way we did the other day, is that if you know that P1, V1 to the N is equal to P2, V2 to the N, you can solve for pressure 2, right? Which I'm going to have them, I wish I would have wrote that somewhere differently. Oh. Thickness, let's write that out. Give me 1 second. I'm going to switch back to the other page. So, let me see if that's what they did. Okay, so they, where'd they find the pressure at? They must have already done it, or they used it from the same questions before. I think that's what they did. They already knew that this pressure was the same one as before, because it was 1.5, right, for the one previously. So they must have already just assumed it was the same pressure, which they're right. Which the pressure was, wasn't it 1.0 something bar? It was like that. Let me go back. Let me see. For values of, is it 1.5? Yeah, it was. So it was 1.06 bar, right? So, but how they did it is the same way I said. You just solve that initial equation for P2, and you just do that. So P1 times V1 over V2 to the N, because remember, both volumes are to the same exponential, so you can put them in together. And so you end up with this at 1.06 bar. Let's go back to 58. So 1.06 bar. So let me go back on here. So we know that pressure 2, I will go ahead and solve that. So P2 is equal to P1 times V1 over V2 to the 1.5. And you just plug in your values that you have at the very beginning, and you get 1.06 bar. And now what I said before was that it is very smart and wise to turn this into kilopascal. So this would be 106, something like that. I think it's 106 kPa. And the other one is 300. And so when you plug this into here, you'll have 300 kilopascal, or 106 kilopascals, right? Times the whatever this is, which is the first volume is this will be 0.2 meters cubed minus 300 kilopascals times 0.1 meters cubed. So you just plug in your numbers here, and then you 1 minus our exponential, which is 1.5. And what you end up with, someone could do the calculation, or I can go back to the page, either one. What you end up with is, where's it at? Yeah, it says, the value of the work for this process is determined in the solution of part A of the previous example. So in the previous example, they get work is equal to 17.6 kilojoules. Using that exact same process that I told you, you get 17.6 kilojoules. And that is, remember, really quickly, this is 17.6 kilojoules, which is in terms of not mass. It is not in terms of time. It is just kilojoules, an energy unit, not mass, which is the reason why we had to multiply in by our mass in the initial one here. We need them to all be the same units. All right? And so, now it's just a simple solution, right? It's a simple energy balance. So, we know as the following. We know that from this original equation, we have M2, well, mass 1 and mass 2 are the same, but anyway, U2 minus U1 is equal to Q minus W. And now that we know W, and we know this quantity right here, we can solve around for the other one, right? Canvas size. Oh, 3,000. Let's try that. As it destroys my whole thing. Jesus. The quality of this program is truly amazing. Alright. So, as I said, now we do that same, we just plug in all of our numbers again. So we have 0.4 kilograms times, remember this quantity in the middle is negative 55 kilojoules, right? Per kilogram. Something like that. And then Q, we do not know, but we do know that W was 17.6 kilojoules. So then, obviously, we just maneuver this stuff around, and we end up with a heat transfer value of, well, you can do this in your head, but I'm not going to, because we have the answer right here. So once you multiply n by 0.4, you get 22 as this value, and then you add 17.6 to it, and you get 4.4 kilojoules as your final answer. So, obviously, we move this down, so it's 22 plus 17.6 is equal to Q. So, this right here, really quickly, I know that took up a bit of time. This question, even though I went through it pretty slowly, this is a question that you will see in this first section on your homework. It'll be a very similar type of question. So, for example, there'll be one that probably does polytropic process from states 1 to 2, or like state 1 to 2, where you have to use this part right here, this volumes and these pressures, and it will tell you to do it at like n equals 1, 0, and all that, right? Then there will be a further questions that show up that have you do what I just did here. It'll have you do, you'll find heat transfer, you'll find the work, you'll find all these things using this exact same process. Now it might sub these out though. It might sub out like, hey, we didn't give you the internal energy change this time. We gave you the heat transfer, right? Or something like that. And then we also gave you the internal energy change, find the work. You see what I'm saying? You can sub these out and they're interchangeable, but the process remains the same, generally speaking. Okay? Hopefully that made sense for everybody in here. Let me see how much further I had to go. for today. Oh man, wow, is that almost it? Let me see. Oh yeah, wow, we are almost done. Where was I supposed to get to today, I wonder? I think it was alternative energy methods. Yeah, that's not. I mean, we'll talk about it, but I don't know if it's super important. Okay. So yeah, this right here is where we're going to leave off. But essentially, this right here is going to be an alternative question. So it's going to be the same question we just did, except now, as you can see here, they've given us other things. They've given us gravity, right? Which means that gravity is now, there's some potential energy effects now, right? They've probably given us some other things here. And they've also given us the internal energy again. They've given you mass, things like that. So essentially, there's other things here that are given that are going to make the question a bit more difficult. But the point is that this is a question that you would see as a very advanced version. I just want you guys to understand that basic one that I just told you. That one that previously is the one. So this is basically the end of the chapter. The rest of this stuff is kind of like, very niche things. Like, for example, we're talking about a gearbox. Like, things like this is something that's very niche. And so I'm not really concerned with stuff like that, but we will talk about it very briefly next time before we get on to the next chapter. But the important part is that the first part, using internal energies, heat transfers, and work, using the polytropic process equation. That is what you'll be doing on your first homework, okay? And your first homework will be posted today, and it will be due by Sunday in the Dropbox at 5 o'clock. Are there any questions about that? And the first homework will cover everything that I have taught up until this point, and probably just a few more. So I think it'll cover Wednesdays and Fridays things. But if you do the questions from Monday and Wednesday, by then you'll get to the Friday ones and you'll be fine. You'll have plenty of time, right? So it will be online by the end of today. And really quickly, if you do have, I know this is going to sound really dumb, but I don't know if you guys are on campus or not. So Dr. Matthias and me are teaching this sort of in the same step. So what that means is that the main class is with us, and what that means is that their homework is going to be same. I'm fairly certain it'll be the same, or it'll be similar at least. All right, I don't know if it'll be the exact same questions, but they will be the same in sort of spirit. And so if you need help and you do have friends that are in the in-person class, you can go to them because they will be covering the exact same stuff we are, okay? So you don't have to, I put this channel together so that you guys can come in here and talk as well. You can go to a study session right here and talk about how to do the homework. You guys all have access to stream in those other channels. So if one of you understands it, you can stream to other people that maybe need help. You guys are more than welcome to do that. But really quickly, that does not give you a license just to give people answers and then have them fail the exam because they didn't know what they were doing. You have to be smart here, guys. Use your head. But besides that, I'm going to take attendance, and then you guys are free